morning, everyone. How are you doing today? It's a great Monday, isn't it? Morning, Moshtaba, Umar, Grace, Lord Melbury. We are on week 14 out of 16, so that means we've got 3 weeks left. It's not much time, but today we are going to wrap up the last session on regular expressions and finite state machines, and then that will cover all the content for the course. And then we got about a week and a half of optional material that we're going to do over the next few days. And then following that, so we got week 14, that's Wednesday of this week, and then Monday and Wednesday of next week, we've got some optional stuff. And then finally, we got week 16, and we'll have no live sessions that week. Instead, I'll be meeting with my students, and we'll be going over the final grades for the semester. So we basically just got 2 weeks left of these live sessions, and then that's it for the semester. So before we dive into the content today, are there any questions? Nope, don't hear any, so let's go. So we left off last time with what are called Thompson's constructions. Now these ones that I've shown you on the screen are just a little bit different than what you're going to find if you do a little bit of searching on the internet, but they're good enough, and I think they work pretty well for this kind of introductory level to regular expressions and finite state machines. So just to review, if you've got two or more things, sub-regular expressions that you want to chain along, you just simply draw them as a sequence of states with transitions. If you have an alternation, you can go one way or the other. In Thompson's constructions, you drew it as two separate transitions that go to the same state, rather than two different branches. And then finally, if you're using the star operator, it's drawn like this. You've got 4 epsilon transitions, and then that one sub-expression there in the middle. So keep those in mind as we do the examples on the next pages. Now, first thing you might be asking, what do these epsilons buy us? I mean, we're able to draw these state machines without epsilons. Why do we have these epsilons in the first place? So let me answer that by having you consider this regular expression, A or B star. So what strings does this accept? Well, it accepts just A by itself. Also accepts the empty string, which you can get by doing 0 B's, no B's, and then any number of B's. So it's either A or epsilon or any number of B's. So the naive but incorrect solution that you might come up with is what I've shown here. And the reason why I say naive is because, well, it involves a loop and it involves a single A. So we've got either an A or we've got like as many B's as you need. And we should probably also make this a final state because we want to allow epsilon. We want to allow no B's at all. But the problem with this finite state machine is that I could do a whole bunch of B's and then I could do an additional A. So that would allow something like BA or BBA as a possible string, but that is not allowed by the regular expression. So this finite state machine allows some strings, or at least one string, that is not permitted by the regular expression, and so that's why I said this was an incorrect solution. So a better way to do this would be to have your starting state, And then, of course, you've got your A. Can't get away from that. And then maybe something like this, where you've got a B transition and then a loop on the end of that. So this will work. You can enter here, and then you could do a single A, and then you're done. Or you could do no B's at all, which you can accomplish by just simply ending on the same state you started at. And then finally, you could do a 1B, or you could do a whole bunch of B's. I need to label this as B. You could do a whole bunch of B's, and you'd be done. So this one works. This one is correct. But it kind of needs some thought and analysis put into it in order to come up with the solution. What we're looking for is a solution that doesn't need a whole lot of thought, where we can, like a computer, to simply look at the regular expression and come up with a solution. Just a sec, I'll be right back. Sorry, it's a little bit windy today, and the wind is blowing my door open and closed. So a solution which doesn't need a whole lot of thought, and we can do that with the epsilons. Here's what we can do, is we could start here at our starting state, and we've got our A. So that's handled nicely. Oh, I didn't mean to make that starting state be an accepting, but we'll see what happens. So what we're trying to do here is construct a finite state machine in which once you make a decision about going down this branch, you can't go back and change your mind. Or once you make a decision about going down a different branch, you can't go back and change your mind. Kind of like having a one-way door that you need to walk through. So that's where the epsilons can come in. So in this state machine, you can accept your single A, and once you get to that accepting, you can't go back and change your mind and do more B's. Or in this one, you can go this way, and then find yourself in that loop where you can do the B's. So this is a good solution also. And we could even take it a step further. We could have our starting state. We could have two epsilons coming off of the start. One of them leading toward the single A and one leading toward the looping B. And this one works too. Again, once you make a decision about which branch to take, you can't go back and change your mind. So that's why these epsilons are handy for our finite state machines, because it makes it easier to construct these machines without putting a whole lot of thought into it. And you can see that once we kind of have this picture, we're getting closer to those Thompson's constructions. So that's why we do the epsilons, and that's also why this Thompson's construction for the A star looks so complicated. Its purpose is to give you two branches to go. You can either take this branch and then loop your A, or you can take this branch and skip over it. Okay, so that's why we're doing the epsilons. They are there actually to make the construction of our finite state machines easier and to be able to do them without putting a whole lot of thought into translating the regular expression into a state machine. What does epsilon stand for? Epsilon stands for the empty string. It's simply a transition that allows you to move to another state without consuming one of the input symbols. So if you're trying to, let's say, match the string BBB, then epsilon allows you to move to another state and not use up one of these symbols. So let's do an example, two examples. We're trying to translate A star B or A into an NFA. And then we've got old friend omnom here. We want to translate om followed by any number of noms into an NFA. So we're going to use Thompson's constructions to do these. Let me walk you through the first one, and then you can work on the other one while I'm doing that. So I'm going to take it step by step. I'm not going to use Thompson's constructions and try to do the whole thing all at once. I'm going to do it a step at a time, and our goal is to end up with a finite state machine, an NFA, that has at most one symbol per transition. But we're going to start out with an NFA that has fewer states, but potentially has more symbols per transition, and then we start breaking those up. So I look at this and I go, what's kind of like the last operation we do, or what's the biggest operation here? And what I see is A star B or A. So these are two smaller regular expressions connected by an or. This is probably the most amount of thought you'll have to do when you're transforming these regular expressions into an NFA, is which operation do I do first? So let's put our start in, and then I'm going to have two branches that end up at an accepting. And one is labeled A star B, and one is labeled A. So I just took this regular expression and put it here, and I put this one, and I put it there. So next, I will break apart the regular expression up at the top. So I got A star B. So that's composed of a sequence of A star and B. That means I'm going to break it up into two pieces. And then finally, I'm going to break up that A star by using that third Thompson's construction, the one that looks like a UFO or a boat. So I'm going to replace these two states with this picture. Okay, so these two became these four. And then I have to finish up with the B and then the A going across the bottom. And that's it. So let's tackle number 2. Here, what I see is om followed by nom star. So I'm going to start with a sequence of om followed by nom star. And then I start breaking them up. So the om becomes two symbols, or two states, two transitions, I should say. There's the O and the M. Here's our start. And then the nom star becomes that UFO. Two epsilons on the outside, and nom in the middle. Then the epsilon that loops back, and the one that skips over. And then finally, we just need to break up that nom in the middle. N, O, M. There's the epsilon. So these two states went there, and then I just broke up the N, O, and M. Then we have our epsilon that loops back, and the one that skips over. And we're done. So we're just successively and iteratively applying Thompson's constructions until we end up with a NFA that has only one symbol per transition. So let's try it with this one. Now, this is the same regular expression that I had over here. Right? I just flipped the A and the B around, but it's the same one. And let's try using Thompson's constructions to transform this into a DFA. So I see B star and A being separated by an OR. So I need to have two branches. And then I break up that B star into that UFO sequence. And the A going across the bottom. It really does look like a flying saucer. And let's number the states. And then we'll transform this using that same cave exploring technique that I showed you maybe last week. So this is our NFA. And then over here, let's do our DFA. All right, so we're starting in state number 1. Actually, so let's say we enter the cave here. We enter this room number 1. But we don't just enter room number 1. We actually automatically zip through to a couple of other rooms. And there's a question here, so is empty string a valid string that this accepts? Yes, it is. So you can see here that we could accept the empty string by just simply going in here and then zipping forward to the accepting, and then we're done. And that's allowed because we're allowed to do an A or any number of B's, including none. So the star operator there says we can do no B's at all, which means we accept the empty string. Okay, so if we enter this cave system, we enter room number 1, but we also simultaneously go to 2 and we go to 4. So if we enter, we're actually going to end up in 1, 2, and 4 all at the same time. So if we are in these three rooms at the same time, what transitions do we see leading out of it? And by transitions, I'm not going to include the epsilon, so only the other labeled ones, the ones with symbols on it. So 1, 2, and 4 at the same time. I see a B leading out, and I see an A leading out. So I know there's going to be a B going out and an A going out. Where does the A go? So if I'm 1, 2, and 4, and I follow the A, I'm going to end up in 4. So I'll write that down. And then if I follow the B out of 1, 2, and 4, I'm going to follow it, and I'm going to end up in 3. But because there's an epsilon coming out of 3, I could also find myself back in 2 again. So again, if I leave 1, 2, and 4, and I follow the B, I'll wind up in 3, but I'll also wind up back into 2. So following the B transition, I'll find myself in rooms 2 and 3. Okay, so if I'm in 2 and 3, what transitions do I see? Well, I only see a B. And if I follow that B out of 2 and 3, I'll wind up in 3 and also back into 2. That means the 2, 3 transition, the B transition out of 2 and 3 loops back to itself. I haven't added any new rooms or new states to this transition diagram, so I'm done. The last thing to do is to mark the acceptings. In my original diagram, the accepting was 4. So anything with a 4 in it in my new diagram is going to be an accepting. That means the initial state is accepting, and this 4 is an accepting. All right, so let's see if it accepts the same strings. Does it accept a single A? So if I enter here, it does. Does it accept the empty string? Yeah, it does, because I just enter, and then I'm at an accepting, so I'm done. Does it accept one single B? Yep, it does. How about 2 Bs? Perfect. 3 Bs? Good again. Oh, wait a second. Something's wrong here. What did I do wrong? Why is it? Oh, I see what happened. Does anyone see the mistake that I made? Does anyone see it? You know, this is supposed to be marked in accepting, but it's not. The mistake I made was, let's go back to 1, 2, and 4. Let's go back here. So I'm in 1, 2, and 4. And if I follow that B transition, right, I end up in 3. And the epsilon says I also end up in 2. But there's another epsilon that takes me to 4. Did you see that? So if I'm in 1, 2, or 4, and I follow the B, it takes me to 3. But the epsilon takes me back to 2, and this epsilon takes me to 4. So this state over here should have been 2, 3, 4. Oh, those epsilon caught me again. And I make this mistake several times every semester, so don't worry about it when it happens. You just have to catch it at some point. Okay, so now we need to complete this. So if we're in 2, 3, and 4, I see a B transition leading out, this one here, and that takes me to 3, and its epsilon takes me to 2, and this one takes me to 4. So it means that this loops back to itself, like it's supposed to. And then this is marked an accepting because it has a 4 in it. So anything with a 4 is going to be an accepting. So this does now accept a single B, and 2 Bs, and any number of Bs. All right, whew, got that done. But you'll probably notice that that DFA that we came up with is identical to the one that we came up with by kind of like thinking about it and trying to figure out how to analyze this problem and come up with a state machine that has no epsilons, but doesn't allow it to accept a string like AB or BA. So it took more steps, but we arrived at the correct solution. We arrived at a solution that's correct. And also, along the way, all we had to do was just follow an algorithm. All we had to do was analyze the regular expression, come up with Thompson's constructions, and then once we had our NFA, just go through the steps of converting the NFA to a DFA, and then we're done. So these are basically the steps that the computer goes through. When you give it a regular expression, it internally uses Thompson's constructions to build the NFA, although it's actually building it in a table. And then it transforms that NFA table into a DFA table, and that gives it the information it needs to be able to essentially write a program to execute your finite state machine and do pattern matching. So let's try doing that process from beginning to end using a table. Now, I'm going to use this regular expression, A star B or A. And this is one that we had used Thompson's constructions on previously, just a few minutes ago. So we already have the diagram for it. All we have to do is build a table out of this. So here's our table. Now, I showed you how to build this table last week, but we hadn't yet put the epsilons into it. Now we're going to build a table that uses the epsilons. So the table is going to look a little bit different. It's still going to have the symbols across the top, but it's going to have one additional column labeled epsilon star. This is the same old star you've seen before, but this one here means 0 or more epsilons. And we're also going to put the states down the side. We'll label the start and the accepting. Here's how you fill it in. So for state number 1, if you're following an A, it takes you to number 5. If you're in state number 1, oops, over here, and you're following a B, it doesn't go anywhere. There's no B's leading out of 1. So we'll just put a blank there. And then finally, state number 1, following 0 or more epsilons, any number of epsilons. So if we're in 1 and we follow 1 epsilon, we'll go to 2. We'll also go to 4. So we'll go to 2 and 4. And if we follow no epsilons at all, we'll stay in 1. Okay? So if you're in state number 1 and you follow no epsilons, you'll still be in number 1. If you follow 1 epsilon, you'll be in 2 and 4. And then there's no more epsilons leading out of those. So that's it, right? If we follow 2 epsilons, well, we can't. We can't follow 2 epsilons. There's only one going this way, and there's one over here. That's it. So what this means is following 0 more epsilons, we find ourselves in 1, 2, and 4. Okay, state number 2. Following an A takes us to 3. State number 2 following a B, don't go anywhere. There's no B's. And then state number 2 following 0 or more epsilons. So we're here. Well, there's no epsilons leading out of it. So following 0 epsilons will just keep us in 2. All right, state number 3. Following an A. Well, there's no A's leading out of 3, so we'll put a blank there. There's also no B's leading out of 3, so we'll put a blank there. But there are epsilons coming out. So if I follow no epsilons, I go back to myself. If I follow 1, I go to 2 or 4. So this is 2, 3, 4. State number 4. There's no A's, so I'll put a blank there. There is a B, and it goes to 5. And then as far as epsilons go, there aren't any, so we'll just do 0 epsilons leading back to itself. And then finally 5, there's no A's, there's no B's, and then there's no epsilons, so we'll just put a 5 because 0 epsilons will keep us there at number 5. All right, so that's our NFA table. One thing you should notice about this table is that under this E star column, you're always going to have itself listed. So you're always going to have at least the state itself listed plus possibly some others. So notice that for state number 1, there's a 1 in there. For state number 2, there's a 2. For state number 3, there's a 3. For state number 4, there's a 4. And for state number 5, there's a 5. So make sure that that column is always filled out with at least itself, possibly some others. Now we're going to transform that NFA table into a DFA table. Again, it's going to look a little bit different. You're going to put A and then epsilon star on top of one column and B epsilon star atop the next column. So you're going to have all the same symbols that you had in your NFA table. You're just combining them with the epsilon star column. Okay, so here's how you fill out the table. First thing you need to know is inside of this table here, the only things you're going to put inside that table are going to be entries out of this epsilon star column, right? We're going to need these entries. We're going to need those, but the only thing that goes inside this table right here are going to be entries out of this column. So here's how you do it. We need to identify the starting state. So we're going to enter here at 1, but we're going to skip all the way over to the epsilon star column, and whatever we see there, that's what we're going to put as our first entry in this new table. And that corresponds to entering root number 1 here and immediately going to 2 and 4, right, by following those epsilons. So we're going to enter root number 1, and we're going to follow those epsilons, and this is where it takes us, 1, 2, and 4. So the first thing we write down is whatever we see under the epsilon star column on the right-hand side of the NFA table. 1, 2, 4. That's going to be our start. Okay, so here at 1, 2, and 4, which means we are looking at this row, and this row. Okay? So we're at 1, 2, and 4. and we're looking at A. So 1, 2, and 4 takes us to 5 and 3. Combine those together. That gives us 3 and 5. So now turn your attention to the 3 and 5 rows and look all the way here under the epsilon star. We see 2, 3, and 4, and 5. 2, 3, 4, and 5. Okay, let me do that again. So we're here at 1, 2, and 4. We're now following an A. So we look into the A column. We see 5 and 3 and a dash, right? Combine those together. That gives us 5 and 3. So now look at the 3 and 5 columns. And now we're following the epsilon star. So we come all the way over to that column and combine what we see there. 2, 3, 4, 5. All right, let's do it again. This time for B epsilon star. So we're following B and then epsilon star. 1, 2, 4. Following B, I see a dash, and a 5. Combine those together. That gives me just a 5. So now look at the 5 row and skip all the way over to the epsilon star column and combine what you see there. 5. Did we add anything new to the table? We sure did. We added 2, 3, 4, 5, and 5. Do it again. 2, 3, 4, 5 on an A. Combine these together. Gives us 3. So turn your attention to the 3 column. Go all the way over to this, the 3 row, I mean. Go all the way over to the epsilon star column and combine what you see there. 2, 3, 4. Now we're going to do the same thing for B's. 2, 3, 4, 5. B. Combine everything you see there, which is 5. Come over to the 5 row. Look at the epsilon star column. Write down what you see. We added 2, 3, 4 as a new state. So we're going to put that on the left. And then keep going. Here's 5. 5A takes us nowhere. Well, that's easy. Just put a dash there. And then 5B takes us nowhere. Just put a dash. Done. Done with that one. Didn't add anything new. So let's do 2, 3, 4. We're doing this one here. 2, 3, 4 on an A. Combine everything you see there, which is 3. So then go to 3 and skip all the way over here and write down what you see. 2, 3, 4. And then finally do the next thing, do the same thing for the B column. 2, 3, 4, B. Combine everything you see there, which is 5. So look at 5 and skip all the way over to the right-hand column and write that down. Didn't add anything new, so at this point we're done. This table is now built. We're going to identify the ending states, so anything with a 5 in it, anything at all with a 5 in it. So it's this one and this one. And then finally, I can show you what the diagram looks like. We've got a starting state of 1, 2, 4. And then following an A, we go to 2, 3, 4, 5. And following a B, we go to 5. And then 2, 3, 4, 5 on an A goes to 2, 3, 4. And on a B goes to 5. 5 doesn't go anywhere. And then finally 2, 3, 4 on an A goes to itself, and on a B goes to 5. Oops. And then this is an accepting, and this one is. So let's see if it accepts the same strings. This one accepts just a single A, which this one does. It accepts a whole bunch of A's followed by a B. So here's a whole bunch of A's followed by a B. How about a single A followed by a B? 2 A's followed by a B. 1, 2, and then this way. 3 A's. Just a single B, which it does by doing 0 A's followed by a B, just this way. So this one accepts the same strings. So that's the whole process from beginning to end. Start with your regular expression. Use Thompson's constructions to turn it into an NFA. Turn that into a table. Transform the NFA table into a DFA table, and then you can draw your DFA. Let's do this one. All right, we already know what this is going to look like because we did it, where is it? We did it over here. But we weren't using a table to do this one. Here we're going to use a table. So we'll take it all the way from beginning to end. So we've got A, B, epsilon star, and we've got 1, 2, 3, 4. Start, accept. Okay, 1 on an A takes us to 4. 1 on a B doesn't go anywhere. There's no B's leading out of 1. And then 1 on epsilon star, 0 or more epsilons takes us to 1. Also takes us to 2, and it takes us to 4. Two on an A doesn't go anywhere. 2 on a B goes to 3. And 2 following 0 or more epsilons just goes to 2. 3 on an A, nowhere. B, nowhere. And 3 following as many epsilons as we can goes to 2, 3, and 4. So here, follow 1 epsilon to take us to 3 and 2 and 4, and then itself goes to 3. And then finally 4 doesn't go anywhere on an A, nowhere on a B, and it goes to itself on the epsilon stars. So that's our table. Next, DFA table. A epsilon star, B epsilon star. Starting state. So we enter here, skip all the way over to this, and whatever we find over there becomes our start. I know I'm kind of going through this quickly. You're probably going to want to watch the recording later on and follow this step by step. 1, 2, 4. So we're here, here, and here. Following an A takes us to 4. So then come over to row 4 and look all the way to the right and write down what you see there. Next, 1, 2, 4 on a B. So combine these. I see a 3. So look on row 3 and skip all the way to the right-hand side. 2, 3, 4. If you wrote down anything new, add it to the left. 4, and 2, 3, 4. Repeat the process. So we're doing this row here. So 4 on an A takes us nowhere. 4 on a B also takes us nowhere. So that row's done. Didn't add anything new. Now this row, 2, 3, 4. 2, 3, 4 on an A takes us nowhere. And then 2, 3, 4 on a B takes us to 3. And then 3 takes us to 2, 3, 4. Didn't add anything new. So table is now done. We just need to identify the final states. Anything with a 4. Anything with a 4 is going to be circled. So that means this one is, and this one, and this one. So we'll do our DFA. We have a starting state of 1, 2, 4. On an A, it goes to state 4. And on a B, it goes to state 2, 3, 4. 4 on an A doesn't go anywhere, and 4 on a B doesn't go anywhere. And then 2, 3, 4 on an A doesn't go anywhere, but on a B it goes back to itself. And then all of these are acceptings because all of these were. And here's our DFA. And notice that it is identical to the one we came up with here and the one we came up with, where was it? See if I can find it. Oh, this one. So maybe the last thing to do would be one that's a little more complicated. Let's do I'll use different symbols too. Let's do G or H star or KH. I don't want to make it too complicated that we're going to be here forever. Yeah, let's do that one. All right. So first step, turn it into an NFA. What I see is this whole left side or this right-hand side. So I've got 2 branches. One of them is KH on the bottom, and one of them is G or H star. Actually, I'm going to add one little bit to it. Okay, I'm going to put a G in the front. Just change things up a little bit. Okay, so the top branch can be broken up into G followed by G or H star. Here's G, and here's G or H star, and the bottom can be broken up into K and H separately. And then finally, this G or H star can be broken up by using the star operator. I shouldn't say finally, because there's going to be one more step after that. So here's G, and then here's the epsilon. Actually, I'll just go ahead and I'll just break that up right now, because you can see how this works. G, H, epsilon. Here's the one that loops back. Here's the one that goes forward. And then we have our K down here. And we've got our H over here. And then let's number these. 1, 2, 3, 4, 5. Whoops, I missed one. Now let's go 4, 5, 6. Okay, NFA table. We're going to have 6 states. 1, 2, 3, 4, 5, 6. Here's our start. Here's our accepting. And we have 3 symbols, G, H, and K. So G, H, and K. And then we've got our epsilon star column. Okay, so 1 on a G goes to 2. And then on an H doesn't go anywhere. And a K goes to 5. And then on epsilon stars, there aren't any epsilons, so it just goes to itself. Okay, now state 2 on a G, nowhere. H, nowhere. K, nowhere. Epsilon stars. I can see here that it goes to itself, and it goes to 3, and it goes to 6. So that's 2, 3, 6. 3 on a G goes to 4. On an H also goes to 4. On a K doesn't go anywhere. And on 0 or more epsilons just goes to itself. Four on a G, nowhere, H, nowhere, and K, nowhere. But the epsilons takes it to itself, and 3, and 6. State number 5 on a G goes nowhere, on an H goes to 6, K nowhere, and the epsilons just take it to itself. And then finally 6 is blank, 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 and then 6. DFA table. We'll do G, epsilon star, H, epsilon star, and K, epsilon star. The starting state, we enter here at number 1, we skip all the way over to the right-hand side, and whatever we see there, that's what we write down for our start. Now, here we got just a 1, so our starting state is just 1. All right, G followed by epsilon star. So 1, G takes us to 2, and then 2 takes us to 2, 3, 6. All right, 1 on H epsilon star. So 1, H takes us nowhere. That's easy. And then finally 1 on K. 1 K takes us to 5. So come over here to 5 and then look over on the epsilon star. So it's like you start here, you go there, and then you go there, and then you make this like the Z shape through the table. All right, we just added 2 new things. So let's put 2, 3, 6, and 5 down on the left side, and then repeat the process. So now we're filling out this row, or this cell right here. So 2, 3, 6 on a G takes us to 4. So come over to 4, and then go over to the right-hand side, and we see that we add 3, 4, 6. Okay, 2, 3, 6 on an H. 2, 3, 6 on an H takes us to 4. So look at 4, come over here, 3, 4, 6. And then 2, 3, 6 on a K takes us nowhere. Blank. We just added 3, 4, 6. So add it to the table and move on to the next row, which is 5. Okay, 5 on a G. So 5G is nowhere. And looking ahead, I can see that 5H is going to take me to 6, and 5K is going to take me nowhere. So I'll add blank, 6, blank. Oh, as far as the H goes, let me do that. So 5 on an H takes me to 6, and then I go here to 6, and I look all the way to the right-hand side, and I see that's 6. So I kind of shortcutted that, filling out this table. So I added 6. Okay, 3, 4, 6 on a G. So 3, 4, 6 on a G takes me to 4. So come over to row 4 and look all the way to the right-hand side and see that that's 3, 4, 6. Okay, 3, 4, 6 on an H. 3, 4, 6 on an H gives me just 4. So come over to row 4, look all the way to the right-hand side, and that's 3, 4, 6. And then finally, 3, 4, 6 on a K. So 3, 4, 6 on a K is nothing. So just a blank there. Didn't add anything new. It's probably a good sign. Once you stop adding new things, you know you're coming to the end. Okay, finally, 6 on a G is nowhere. On an H is nowhere. On K is nowhere. So blank, blank, blank. And then nothing new. Anything with a 6 is accepting. This one, and this one, and this one. So let's see if we can cram our DFA into the corner. So we got our start state, which is 1. On a G, it goes to 2, 3, 6. And on a K, it goes to 5. 2, 3, 6 on a G goes to 3, 4, 6. I'm looking right here. And then 2, 3, 6 on an H also goes to 3, 4, 6. Uh, 5 on an H goes to 6. And then 3, 4, 6 on a G goes to itself. And on an H also goes to itself. And then that's it. So the acceptings are 2, 3, 6, 3, 4, 6, and 6. So you look at this DFA, and you can probably see that, you know, this is not entirely necessary. We don't really need this. We could have just like looped that and looped that. But that's where you could have like DFA optimization. And we're not concerned with that in this introductory course. Okay, so we went that way, and then we turned it into that, and then we went that way. Kind of made a big circle around the screen. So let's see if it accepts the same strings. So does it accept just KH? Boom, boom, right there, got it. Does it accept G by itself, which you get by doing a G and then none of these? Right there, perfect. How about a G followed by G? GG. So right there. GH. Good. How about a G followed by a G followed by an H? So we can do a G and then a G and then go, remember it loops back, and then we can do another H. So G, G, H, good. We could also do like G and then GH, GH. G, G, H, G, H. Yep. So it appears to work. So again, that's the whole process from beginning to end. Start with your regular expression, apply Thompson's constructions iteratively until you end up with an NFA that has one symbol per transition. Then from that, construct your NFA table. The NFA table is going to contain all the same information that's in the NFA. And then there you can turn the NFA table into a DFA table. And then finally, you can turn that DFA table into a state diagram. Now, if you do a little bit of searching on the internet, you look up Thompson's constructions, you'll find that there are tutorials or reference diagrams that have something a little bit different. So instead of just, like for the concatenation, instead of just a sequence of 3 states, there's also these epsilons sitting on the sides. And the same thing for the alternation. There's these epsilons sitting on the sides. And even the star also has epsilons sitting on the sides. They're kind of like, you can picture them as being kind of like the couplers that hold railroad cars together. And so the idea there is that if you have a regular expression like A or B star, you write down the construction for just a single A, which looks like the single A with the epsilons on the other side, on either side of it. And then you write down the one for the B star, which looks like the UFO operator, and then you connect them with these epsilons, kind of like, again, like couplers in a railroad car. And so what you see here is just an explosion of epsilons. Like for every single symbol that you're going to write down, there's going to be at least 2 epsilons, which means the number of epsilons doubles every time you add a new symbol. So there's going to be a huge number of epsilons, which is going to make your, you can still transform it into a DFA. You can still write down your table, except your table state names are going to be like long sequences of numbers, right? Because the epsilons could take you to maybe 5, 6, or 7 states or more. So there's just going to be a huge number of epsilons. It just makes the process a little more complicated, but you still go through the exact same analysis and the exact same steps. So that's why, for my purposes, I simplified the Thompson's constructions a little bit, eliminated some of the extra epsilons that we don't need, at the expense of having to put a little more thought into transforming the regular expression into the NFA. Is there a variation of this that uses a binary table? I don't know the answer to that. Is that something you've seen, or just curious? Because I've not heard about something that uses a binary table, although I'm trying to figure out like what would that look like. So I don't have an answer to that, unfortunately. Oh, just curious about it. Yeah, I don't know. So for those of you who are in my course, I have one more assignment for you to do. I haven't put it together yet. I will basically have that ready, hopefully by Wednesday. It'll be what I just basically did. You'll start with a regular expression and then go through the process of transforming it into an NFA and then a table, and then transforming that NFA table into a DFA table, and then finally drawing your final DFA. You'll do that a couple of times, and that'll be the last assignment for the semester. And then that'll be it. So this is all the content for this course. We've reached the end. So where did we go? What was our journey from here, from the beginning of the semester to the end? Well, we started with just learning about how to represent data using binary and different bases, like base 32, base 64, hexadecimal. And then from there we went into Boolean logic and circuits and how to build a computer from its fundamental building blocks using these logic gates. And then we started talking about modular arithmetic, and that led us up through cryptography. So we learned about how to add and subtract in modular arithmetic, do exponents, and then we learned how to encode and decode using the shift cipher, linear cipher, and that ended up with doing RSA. So we ended up using a really modern cryptography technique, but on pen and paper, or small Python programs. And that took us up through the first half of the semester. Then we started on things like sets, probabilities, combinations, permutations. And that led us towards finite state machines, regular expressions, graphs, and then that's where we ended up. So we covered a huge variety of topics. And the topics that we covered is a little bit different. Actually, I won't say a little bit different, a lot different than what would be covered in a discrete math class. A discrete math class is going to be more on the, I should say, the theoretical side rather than the practical side. So you might have talked about cryptography, but you certainly wouldn't have written a program to do it. You might have talked about maybe a little bit of graph theory, but again, there might not have been a connection between the theoretical graph stuff and what you do in everyday life with Google Maps and regular expressions and finite state machines. I don't think a discrete math class would have talked about number bases, except maybe just as a kind of a, oh, by the way, kind of something on the side. So I really like to take the important concepts out of a discrete math class and apply them to computer programming. And that's what makes discrete structures. So it's a little bit different than discrete math, a little more on the practical side. We don't cover some of the topics that discrete math does cover, but we also cover some additional stuff. So that's the content for this course. And there's a book I have back here called Foundations of Computer Science. You can get this book for free online now. This big, huge book, about almost 2 inches thick. And this dates back to, let's see, what's the date on this? This particular edition is 1995. So we're looking at, what, about 30, 35 or more years old for this material. And it kind of dates back to before we even called this discrete math or discrete structures. But if you look at the table of contents for this book. So this was written by Alfred, I don't know how to pronounce his last name, Aho, and Jeffrey Ullman, who were 2 influential computer scientists back in the 80s and 90s. But you look at the table of contents and we have things like, I gotta take off my glasses to read this here. Well, first, chapter 2 is proofs by induction and recursion. We did a little bit of recursion, right? We talked about how to write recursive functions like greatest common divisor and sorting. I think, did we cover sorting in this? I don't remember. Oh, anyway. But anyway, they talk a little bit about sorting and then running times of programs, so big O notation. We don't cover that in this discrete structures course, but we do get it in some of the other courses that I teach, like the C programming course and Java programming courses. We do talk about running time analysis of some common algorithms. Combinatorics and probability, there it is. Tree data models, so we do talk about trees. List data models, we do talk about arrays in this class. Sets, we talk about sets. Relational data models, we don't do that so much. So there's one chapter we don't cover. Graphs, patterns, automatons, and regular expressions. So there we go. Propositional logic, which is basically Boolean expressions. And then using logic to design computer components, gates, circuits, and so forth. And then finally, predicate logic, which we don't cover a whole lot. But I would say out of the table of contents for this book, we probably cover 2/3 to 3/4 of the material. And this was before it was called discrete structures or discrete mathematics. Well, discrete mathematics existed, right? But so I looked at this book and I went, you know, this pretty much covers all the stuff we need to cover in a discrete structures course, or discrete math course, right? But with applications to computer science. So I kind of modeled my curriculum off of this. Now, what this doesn't cover is cryptography. I think that's really cool, so I included that in my course and didn't have so much on the things like proofs. So a discrete math course is really heavy on proofs and more proofs, and discrete structures is a little lighter on that. So that's where I got the ideas for some of the content for this course. Well, we actually reached the end. We have finished a little bit early. Are there any questions? One of the reasons why we finished a little bit early is normally if I was in a actual classroom setting, we would have done these problems that I just showed you, but we would have kind of walked through it step by step. Instead of just me showing you how to do the problems, I would have had you put the problems on a piece of paper and we'd walk through the problems step by step, and I'd have you like give me the answers as we were solving the problems. But it's a little harder to do in this Zoom, YouTube environment. So I just walked you through the problems and then go back and watch the video, go through it step by step, and you'll be able to replicate those steps on the homework assignment that's coming up. Okay, so that is it for today. Thank you, Grace. Thank you for thanking me. And I hope you have a good rest of the day. Remember to come back on Wednesday and then Monday and Wednesday of the next week for some of the other material we're going to cover. I think it'll be interesting stuff. We'll talk about like quantum computing, and you know, I might spend a day. You can barely see it in my cameras here, but I have like, oh, there we go, like these old computers back here. Show you a bit about how to program those. And I don't know what else we'll cover, so we'll see. But it'll be like related material to the stuff in the course. Okay, so if there aren't any questions, then we will end it there. And I'll see you on Wednesday. Okay, take care. All right, bye-bye. And then those of you on YouTube, remember I have the Monday, Wednesday class, which is, and I think on Wednesday we'll probably talk about quantum computing. But I have my Tuesday, Thursday class, and you might not want to miss Tuesday's class, the one tomorrow. I've been working all weekend on this, and what we're talking about in that course is computer networking right now, how one computer can interact with another computer. So I'm showing you how to write programs in C to send data to another computer and receive responses back from it. And you're basically writing the client side of a client-server interaction. But what I was working on all weekend was how does the data actually get sent from one computer to another? Like what goes on when you have let me reach over here and grab this. You know, what happens when you have an Ethernet cable? What goes on in these wires inside here? And so I was working on this weekend is how can we analyze the actual ones and zeros going across this wire. So you might want, I'm actually not going to use Ethernet. Ethernet goes too fast. It's gigabit speeds or 100 megabits. It's just too fast to like watch the signals go across. So I was able to come up with a way to slow it down so we actually see the ones and zeros appear on a screen and then decode those ones and zeros and see the actual bytes being sent. So that's what we're going to do. We're going to do there. So we won't actually be looking at Ethernet signals. We'll be looking at serial line signals. And I think it's going to be really cool. So that's what I've been working on this weekend. And I'm really kind of proud of what I came up with. So that's why I'm tooting my own horn here. So that'll be on Tuesday. That'll be tomorrow. Okay. So if there aren't any other questions, Lord Milbury, no, it does not use Manchester encoding. Manchester encoding is used for Ethernet, but we're not going to be analyzing Ethernet. It's a little too complicated. There are some great videos out there. I think there's one by Ben Eater, E-A-T-E-R, in which he actually does analyze the Ethernet signals. And so that's really cool to watch. He actually was the inspiration behind what I was doing. But I don't have a good way of just sending raw Ethernet packets. I mean, I could, but there was more work than I wanted to. So I came with the idea of just using serial cables, and those are easier to analyze. So we'll do that. Okay, so I think we've reached the end of today here. I'm glad you can make it. I'm sorry I spent all the time talking this time. Normally I would get your input on something, but it looks like I think I answered your questions. And come on back tomorrow. Come on back on Wednesday. And we'll do more stuff. All right? Well, have a great day, everyone. I hope you stay safe. Take care. Be well. And I'll talk to you later. Bye-bye.